Good wishes Physics 103. This is lecture 5A1, in which I will introduce a new character called the displacement vector D. And so the D vector. The motivation is introducing to this vector, which helps us in analyzing problems in the dielectric. This is called the displacement vector. Okay. So we know that we can control the free charge or potential that we can put on a body or material. Okay. For example, if I have a conductor, okay, and then apply an electric field, then it responds by moving its electrons to the surface in such a way that electric field is equal to 0. In the process, the electric field outside itself gets modified. So this is the response of a material when electric field is applied. So in other words, a conductor responds by finding a charge distribution that makes the electric field inside it 0. In the process, E outside gets changed accordingly. Okay. How about a dielectric? So for example, I take a dielectric slab and put it inside a parallel plate capacitor. Okay. Then I'm applying an electric field from outside to this battery. Then how does it respond? We know that it responds by producing the bound charges, okay, inside it. So for a dielectric, we have already seen this. It responds by producing bound charges either in the surface or in the volume of the body. And the net field is determined by both free charges and bound charges. Bound charges depend on the properties of the dielectric and its shape as boundary conditions. Okay. So if I can't control the electric field, so which means I can't control, because there's a response of the material also involved. So the question is, if I can't control electric field, can I get a vector that is primarily due to free charges which I'm able to put through my battery or by fixing the potential? So is there a vector? Because E doesn't seem to be under my control. The conductor has the ability to change it. The dielectric comes up with own bound charges. So with material response, my E seems to get changed. So how do I get to know something which is independent of the response? Okay, and then I can calculate if I can calculate polarization P and charges and so on, and then finally electric field. If I know all the charges, then how do I know how much is polarized? So if I only know if there is a vector which is directly under my control and responds only to free charges. All right, so that's the motivation. So let's start with Gauss's law in presence of dielectric. Okay, for example, that's the one way of dealing with bound charges. We know that in a dielectric, we may have both free charges, for example, electrons and ions, and also bound charges due to polarization. And hence, the Gauss's law would include all the charges. Both determine the electric field. So total charges, charge density is then rho, okay, is a free charge and bound, where rho f is the free charge, and rho b is the bound charge density. And I can write the Gauss's law in that case, okay, very simply as epsilon naught divergence of E is rho total charge, free charge, and bound charge. I've just that epsilon naught I've taken on this side, all right? Then I can rewrite this because I know what is bound charge, what is the relation to bound charge, and that is epsilon naught E plus minus divergence of the polarization P. Now there is one divergence term here and another divergence term here. Obviously, I should bring them together. So if I bring them, collect the divergence terms, then epsilon naught E plus, okay, so that will give me this, okay. And obviously, I should now combine these two divergence terms, okay, and take the divergence out, and then becomes epsilon naught T plus P. Now this seems to be a new vector. This is a vector. This is a vector. This seems to be a new vector whose divergence is only free charge. And that has been the whole intention. All right. So Let me write that down. So now defining the displacement vector as this quantity, okay, epsilon t plus p, that's the d. And so in the differential form of Gauss's law then becomes simpler, okay, because the bound charge is not included. Now divergence of d is simply the free charge. This is the source. So d is the source of d is rho f. That's what divergence is supposed to mean, right? The free charges only. And if I take an integral with the volume, and then I can use the divergence theorem and get to the surface enclosing that volume, then d dot dA is the total free charge enclosed within that volume. Okay, this is so only free charge. That is what I meant. All right. So, and what is the d? Of course, units of Coulomb per meter square, which is the same thing as sigma. All right. Uh, Now, d vector is invaluable in presence of dielectrics and bound charges. Okay, in this whole chapter, we'll see that. Now, why is it named called displacement vector? Okay, answer to that question I will give in the next half when we discuss Ampere's law. Okay, when we're discussing magnetostatics. Okay, so but they're dielectric materials. So, what property measures how polarizable dielectrics are? Okay, so then there is polarizable, meaning that the polarization vector P in response to E. And so P is produced in the material, the function of E. So this is called a constitutive relation. Okay, that is, this is external, and the material's response is a constitutive relation. It produces polarization, and this chi E is called a dimensionless material property called the electric susceptibility of that particular medium. All right, and if P is directly proportional to E, which means chi E is simply a constant, okay, then we call it a linear material, because P and E will be the function of P and E will be the magnitude would depend only on electric field, and it will be linear. So this is a linear material. So if chi is a constant, the material is called a linear dielectric, and P versus E has this constitutive relations. All right. So D, but we know D epsilon is P, so I can now replace P by chi E epsilon naught E. Okay, and now epsilon naught E can be taken common. Okay, so then all the material properties in this quantity, 1 plus chi E, and that we can call it as relative permeability of that particular material, which is epsilon R. And if we multiply epsilon R into the permeability of the vacuum, that is the epsilon without any subscript. All right. So this is the permeability of the of the medium. All right. So this is the definition of relative permittivity, simply 1 plus chi E. Sometimes use chi E, sometimes use epsilon R, whatever is convenient, wherever. This is just the ratio of the permittivity of the medium divided by the permittivity by vacuum. That's why it's called relative permittivity. For common semiconductors such as silicon or gallium arsenide, epsilon R is of 10 per 12, meaning they're quite polarizable. Whereas like an insulator, like silicon dioxide, which is used with silicon industry very much, is not so polarizable. So insulators are typically 4, okay, the relative permittivity. Diamond, a little bit more polarizable, is 5.6. Now water is 80.1. All right, I mean, I'm saying completely pure water. Um, there are substances which can have epsilon R as high as 50,000 or 80,000. Okay, but many of them are not linear dielectric, so I have not included it here. So, which means is they are extremely polarizable, or maybe they're already polarized. Okay, but those are non-linear. So if chi E itself is a function of E, then it is called a non-linear dielectric. And this is as in ferroelectrics, piezoelectrics, or pyroelectric materials, and other such non-linear crystals. But in this course, we deal only with linear dielectrics. Let's take an example, example 5A1, in which I consider a parallel plate capacitor with a dielectric inside. So dPe, how does that work out in a parallel capacitor? Okay, I have applied, let's say, sigma f, and so assume that the charges on the plates are given. Sigma f is q by a, and the relative dielectric constant of the is epsilon r. Okay, so it will respond with bound charges, of course. So now, how do I plot what is the d? D, remember, depends only on sigma f. So if I take a Gaussian, which includes, let's outside it is zero, the field is zero, because the effect of this plus charge and this minus charge and all the effects is zero. So I can take a Gaussian cylindrical surface with one face here and one face inside the inside the material. Okay, it will not matter the bound charges, only what will matter is sigma f, and hence this, the whole of d in between the plate will be a constant, because it only depends on sigma f, and by using Gauss's law. So if I take d dot a and then qf enclosed, and then I will simply get uh, and I know that epsilon naught is p, and that is 1 plus chi e, but d simply depends only on sigma f, and hence d would be just constant depending on only on sigma f, the free charge. All right. How about polarization? Because now there is a d, d would produce e would, there will be e, and that will produce polarization. Okay, so polarization is of course zero outside the dielectric, because there is no dielectric and there is no polarizable material here. And then as we enter the dielectric, the polarization increases, but the polarization would be how much? 1 minus, suppose epsilon r is 4. Okay, then 1 by what? 3/4 of d. So this is less than that, less than d, because of the, okay, so now can I calculate the epsilon naught E, which means electric field? That of course is simply d minus p from here, okay, or d minus p, and hence I can plot now epsilon naught E as a function of x, okay, and that is of course there is full d and e are here, epsilon naught E are the same here, there is no, okay, in this area, and then once we enter the material, then it gets reduced by amount, by what amount? By p amount. Epsilon naught T gets reduced, and hence it gets reduced and then joins up again to the same epsilon naught E as dictated by the d here, and then of course reduced to zero. So and where are the bound charges? Of course only here, okay, and only here. So I could have plotted also a sort of a delta function of bound charges, negative going here and positive going here. That's the bound charges. That's a complete electrostatics of a plane parallel capacitor with a dielectric. How much is the charge? Sigma b is 1 minus epsilon by sigma f, which is less. Okay, typically epsilon r is larger than 1, and hence the bound sigma charge is sigma f, and that is less. So note that sources of d are free charges. Okay, that's what I wanted to illustrate through this example. Sources of p are bound charges, okay, which is only here. Sources of e are both bound charge and uh, discharge, and in this case the direction of d and p are the same. Okay, so rho b is minus, of course is a linear homogeneous dielectric, so the rho b is zero. Okay, there is no divergence, and so you cannot argue on physical grounds why the capacitance is larger with dielectric inside. Larger the dielectric constant, larger is the capacitance. Okay, so convince yourself that introduction of a dielectric indeed increases the capacitance, not just on the basis of formulae. Okay, in terms of physical mechanism. The next example that I take is a coaxial cable, okay, and which is a very an extremely important piece, which you sometimes might neglect in a lab because it doesn't look like a heavy instrument. But this is of extreme use in all our laboratories in whatever discipline, and you might have seen them, okay, in your audio amplifiers or connecting TV and so on and so forth. So between two connectors, what is there is a coaxial cable, okay, such that signal gets transmitted from one place to another. And why is this important? This is important because this ensures that high quality noise, so high quality signal gets transmitted, and noise from outside is not does not get into it. Okay, and then how does it look? So this is called a B and C connector. Okay, Barnett, N and C are for the inventors. Okay, so called B and C connector, which goes and locks into the instrument. But what is connected to is the coaxial cable. Okay, and what does the coaxial cable consist of? Of course, there is a black jacket. Okay, and the number of the coaxial cable is typically printed at the end, RG59, and then inside that there is a B, is a copper braid, and then there is the plastic, okay, which is a dielectric, and inside is the actual conductor, copper conductor, solid copper conductor, which does the transmission of the signal. Okay, so core, uh, so you have a core, then you have a dielectric, which is the insulator, then another metallic shield, and then on top of the plastic jacket. That's what typically a coaxial cable looks like. Okay, and if I take a cross section again, so there is the conductor inside, then there is a dielectric surrounding it, and then there is a metallic braid or copper braid, and then there is a jacket. That's the cross section. Now, this was a particular coaxial cable was invented by a person. Uh, a person, which is Oliver Heaviside, okay, and we owe a lot to this person, okay, not just because he invented coaxial cable. He was an electrical engineer who was deeply involved in telegraph. He wrote, he read Maxwell's treatise on electrodynamics or electromagnetism for years, and then he found it tough to communicate. He was excited by it, but he found it difficult to communicate to other people his excitement or understanding of Maxwell's equations, of the way Maxwell treated electromagnetism. And he's the one who brought vector calculus to electrodynamics and rewrote Maxwell's equations and named all the quantities properly, and all the names we actually owe to him. Okay, impedance, assistance, and so on and so forth. So he rewrote. If Maxwell was supposed to read Griffiths today, he won't be able to make head or tail of it, because he did not know, or he did not write his treatise with vector calculus. It is Oliver Heaviside who did that, and it is on his footsteps that even the modern things, modern books are written. He was a remarkable, not just an electrical engineer, but a mathematician and a physicist, and contributed in many ways. He brought complex analysis to electrical engineering, circuits to be analyzed using complex analysis and the differential equations solutions through Laplace transform. Okay, he brought to electrical engineering a significant contribution. And in mathematics or electrical engineering, you're also going to encounter with Heaviside functions. Okay, there are many contributions by him. Okay, I just included that, saying that we owe a lot to this man in for the modern form in which we are studying electrodynamics. Let me go on with the coaxial cable example. So this is an example. There is a conductor core of A, and then from A to B there is nothing. Okay, it is, you can consider it as vacuum, and then from B to C it is a dielectric, and then outside it's a copper conductor. Normally it is grounded. Okay, the way you connect it, that is grounded. So there is a copper at the outer shield. Then there is so let's look at the problem. What the problem says. Problem describes the situation, but the problem is about finding out capacitance of a long coaxial cable. Okay, that is capacitance per unit length, obviously. So a coaxial cable consists of copper core of radius A, surrounded by a concentric copper tube of radius C. The space in between is partially filled with a material of dielectric constant epsilon r. Okay, and so what is our task? Our task is to find the capacitance per unit length. Okay, so how do you go about doing that? So there is a strategy. Strategy is to put a free charge on the central conductor, okay, on the inner cylinder, and then obtain D everywhere, because D depends only on free charge. There will be bound charges, but I will not be worried about it. Okay, and then from there D I can get now E, knowing the material properties. Here, for example, epsilon R, and this is vacuum. And once I know E everywhere, I can calculate the potential in, okay, and that will come out in terms of the free charge that I put. And once I know potential V and Q, I can obtain capacitance C. Okay, so that is the strategy. So let's calculate. So let's take any Gaussian cylindrical shape Gaussian, okay, around it, and then well, let's say with a radius s, and it could be anywhere, okay, and a length L, and so ds and L is the area, so d2 pi, so, and its total is the free charge is only q, and hence d simply is q2 pi sl. All right, and hence for I can now find out E. Once I know E and D, I can find out E between A and B. Between A and B, this is free air, and hence is epsilon naught, q by 2 pi epsilon naught SL. This is D by epsilon, and in this case, epsilon is epsilon naught. And then between B and C, I simply put epsilon, because there is the dielectric is there. Okay, so knowing D, I'm being able to produce E everywhere now. Okay, so this is what I want you to notice. Okay, so knowing alone, I can now get E in all regions. Once I know E in all regions, I know it is a grounded conductor outside. I can now get the potential simply by line integral E dot dl. So from C to A, and that is, I can integrate from A to B. That is epsilon naught SL. So remember, ds by s appears here. From B to C, again ds by s. Okay, but except that here it is epsilon naught, here it is epsilon. Both will give me log terms. So I'll use, so the first term will give me log BA. I've taken epsilon naught common. So I'll have a epsilon naught by epsilon here, and log of C by B. Okay, and hence I've got my potential. I can write down the final potential, and hence C is equal to Q by V per unit length. That is in terms of all the geometrical and material properties that is given, A and B, B and C, epsilon naught R. That's the dielectric property of the dielectric that I have included here. Okay, so capacitance per unit length. This is very important in most cases, because the signal transmission depends on the quality, and but every time I introduce this into the circuit, there is new capacitance. Okay, and I have to worry about that capacitance, and is an important consideration for the choice of coaxial cable depends on the capacitance per unit length. Okay, so we will get back to the next part of the lecture in another video.